This is lecture 8 of CS147 computer architecture study. We have like two sections today. One is a sequential circuit design. Uh, in last lecture, we were introduced with sequential circuit concept and the storage element which needs to be used for sequential circuits. So we'll see how from a given problem we can implement a sequential circuit. Okay, that is the first part. Second part will discuss commonly used digital circuit components that we will be using to build up a complete processor in this class. So there are many digital circuit components. We don't need all of them. We just need to get familiar with those components which are majorly used inside processors. So we'll review them one by one. Now to start with these topics, right? As I was describing, sequential circuit design is one part, and another is digital circuit component. We have couple of components there: decoder, multiplexer, register, shift registers, and barrel shifter. So we'll look at each of these component. What's their functionality? How they're built up from using logic gates, either combinational or sequential. Uh, then after that, once we know these components, then we'll shift our discussion from next lecture onwards on how to build a processor. Okay. Now sequential circuit design. First of all, let me tell you, sequential circuit design is not very easy. Okay. And secondly, at least one of its step is not I would say it's not very well defined process and steps, but it's more, I consider more like an art than a science. One of the step, I'll explain it. But once we achieve that step, then rest of the design process are more or less like streamlined. It has steps and what to do and what not, right? So like combinational circuit design, we start with a specification, right? Collect and write the specification, and then formulation, obtain a state diagram and state table. So this is the step I was referring. It is not an exact science, but it is kind of an art. So over the time, with experience from a specification, you can actually come up with like efficient state diagram, which leads to smaller circuit, digital circuit. Uh, in other word, like there is no one answer on this step. Like from a specification, like different persons can come up with different state diagram and state table. Okay, so some of them are very efficient, means from like circuit perspective, like they from that type of state diagram you can derive very small and compact digital circuit. Other may become a really out of control huge circuit and stuff like that. So it's basically comes with the experience. You need to practice a lot with a different problem to actually get hold of this specific step. Okay, but nonetheless, I'll explain what that state doing through an example, and you can kind of follow through the similar approach of solving problems. But again, it is very problem specific. There is no like scientific formula or like algorithmic step that I can tell you that you follow and you will come up with a state diagram. Okay, so you need to practice a lot that step. Now once we are done with the formulation, rest of the steps are pretty much defined, pretty much algorithmic. So you can follow step by step, almost blindfolded. Okay, so state assignment, we'll discuss that. It is to assign binary code to the state and convert the state table to the truth table. Once we have truth table, then we can solve that truth table with the k-map. Here only difference is that we need to come up with the flip-flop input equations. Now optimizations and technology mapping verification, these are all like is common step with the combinational circuit design. All right, so these are the steps. Now let's take an example. Okay, let's build a sequence recognizer as one input, let's mark it X, and one output, let's call it Z, and it has a reset applied directly to the flip-flop to initialize circuit to all zeros, and so we can reset the flop. So as we are talking about this flip-flop, that means we are assuming there is a clock signal as well. All right, it is not mentioned here, but the flip-flop has a reset and clock signal. Now this circuit should recognize the occurrence of sequence of bit 1101 on incoming bit stream through X. Once a pattern 1101 is recognized, output Z should produce a 1, otherwise output will remain 0. So imagine like each clock, each tick, our input is incoming on the X. Okay, so each tick it is either 1 or 0, or like it may be like 11111011100000011, something like that. Over the time, this one bit sequence of 1 and zeros are coming and being presented to the circuit. So what Z is telling us at the output side, that if it become 1, that means it has received a sequence 1101. Okay, otherwise if it stays at 0, it says that okay, it hasn't received any 1101 from the last time it got a 1101 or from the beginning. Okay, so if it is a 0, it can mean either it didn't get any 1101, that sequence in the whole sequence of bit stream coming up from the beginning, or from the last time is recognized 1101. Okay, that's what the Z is. Okay, now let's make a state diagram, like formulation of that whole problem in more formal way. So let's say I define a state called A. Okay, and upon reset it goes to state A, the whole machine. How the state is implemented, what is the digital implication, that's a different thing. Okay, but somehow let's say we can mark in a machine a state called A, and upon reset that digital machine goes into a state A. Okay, now inside state A, if I get a 0, okay, the first side, like before the forward slash, that part is like a input sequence. Like since this circuit has only one input, so we see one bit there. If a circuit has like multiple bits, like 2 or 3 bits, we'll see 2 or 3 bit before the forward slash. And similarly, after the forward slash, this bit is basically what my Z is, what the Z value is at this condition. If there are more outputs, like 2 or 3 outputs, we'll see 2 or 3 bits after the forward slash. So before forward slash, that part is the input bit pattern, and after forward slash, that part is a output bit pattern. So in a state A, so what this diagram so far is telling, upon reset, machine enters into state A, wherever it is. Okay, secondly, on state A, if my input is 0, my output will be 0, and I will remain, this machine will remain at state A. Next, this arrow, follow through the arrow. Now, and the mark on that edge, on that arrow, is that is now from state A, if my input is 1, my output will be 0 and my state will be B. Okay. Similarly, we keep on doing this thing, like now from B, if I get a 0, my output is 0 and my state, I'll go back to state A. Okay. So this thing, instead of going to state A, going to state B, let's introduce this term next state. Okay. Again, from the beginning, what is happening? On reset equals 1, my next state is A. Okay. Sometimes we refer it as a reset state. Now from state A, if input is 0, my output is 0, next state is A. If from state A, if input is 1, output is 0 and next state is B. From state B, if input is 0, output is 0, next state is A. Okay. Now on B, if my input is 1, then output is 0, next state is C. Okay. From C, if input is 1, output is 0, next state is C. From there, if input is from C, if input is 0, output is 0, next state is D. From D, if input is 1, then output is 1 and next state is B. From D, if input is 0, output is 0, next state is A. So you might wonder what is going on, right? It's just a bunch of state transition on the inputs and so on and so forth. So thinking process is this, behind this, coming up with this state diagram. It's this. State A, I designate that as a 0 has been seen so far. Okay, a 0. Because if it is like sequence of 0, 0, 0, 0, it is not of my interest, right? It is not going to contribute to the pattern 1, 1, 0, 1, right? So I'm getting 0, I'm being at state A, I don't know, like I have seen 0 so far. Now, as soon as I get a 1, I switch the state, making the output 0, but switch the state to B, which denotes that I have seen 1, like this machine has seen 1 so far, so it may contribute to my 1101 sequence. Okay. Now from that, if another 0 comes in, that means it's not going to contribute to 1101 pattern, right? So I go back to A. But from B, if I get another 1, so I probably may going to see an 1101 pattern. So I switch it to the state C, which kind of tells that 1, 1 has been seen. Okay. And from there, as long as I'm getting another 1, so there is a possibility, like it can be like 1, 1, 1, 1, 1, 1, and then 0, 1, right? So as long as I'm in C, which is like 1, 1 has been seen, another 1 or successive 1s as I get, I keep on staying at C because it can contribute to that 1101 pattern, right? And then as soon as I get 0 from D, then I switch to D, which tells me I have seen 110 so far. Now from there, I can either receive 0 or 1, right? So if I get from state D a 1, that means, hey, I hit the 1101. I got it. Okay, so I make the output 1 and move to B. Why I move to B? This 1101, the last one, can be beginning of the next successive pattern, right? So in the problem statement, it did not say that this pattern cannot overlap, right? So it can be a pattern like 1101, 101, 101, something like that. So it's all overlapping 1101 pattern. So That's why I switched to B, because B says I have seen a 1. So it might be start of another overlapping 1 1 0 1 pattern. But if the problem statement would have said that it is a sequence recognizer for non-overlapping 1 1 0 1, then I should switch to like a reset state, like a. Okay, start from beginning and follow through the pattern. So that's what the state diagram would change in that point. Now come back here, like on the D110 has been seen. So now I get the 0. So 110, it's not going to take part in the sequence. It's not going to like be another B or C. I need to go to A, because that's what saying that I have seen a 0. So now you feed me 0, I will stay there, and as long as you are feeding me 0, I'll be at A. As soon as there is a 1, I'll switch to B, in hoping that I might again get into 1101 sequence. So that's the thought process behind coming up with this state diagram. So you may think in a different way, can come up with another different state diagram which perfectly can work. Okay, so no one unique answer here. So this is one of the state diagram that will serve my purpose.